Welcome to this Masterclass Explainer. I'm your lead dev for today, and listen, we are treating this session exactly like a Silicon Valley hackathon. Okay, let's just dive straight in and fix the absolute biggest glitch that's currently crashing the Cambridge Mathematics 9709 mainframe. Our target system? Trigonometric reciprocal functions. Yep, we're talking sec, cosec, and cot. For years, students have been treating these functions like simple, raw calculator inputs, and honestly, it's resulting in massive logic errors on exam day. So, today, we are going to completely rewrite your approach from the ground up. We're going to treat your exam paper not as some static math test, but as a dynamic algorithm that can be solved with perfect, code-like syntax.
Now, this critical system alert is straight from the Cambridge Principal Examiner reports. It shows us exactly where students' exam logic is crashing, clearly stating that sec, cosec, and cot functions represent one of the most fundamentally misunderstood areas in the entire mathematics syllabus. Crazy, right? But why is this happening? Well, it's because students try to just brute force the math without actually understanding the underlying architecture. They memorize that secant is 1 over cosine, but they totally miss the causal relationships, or how it behaves in unfamiliar domains. So today, we are going to patch that exact vulnerability.
All right, so here is our boot sequence. 1. We diagnose the trig system bug. 2. Define the syntax and architecture. 3. Debug examiner mistakes. 4. Map the problem-solving algorithm. And finally, 5. Compile your final code.
Okay, kicking things off with Section 1, the trigonometry system bug. Let's examine the theoretical architecture of our target mainframe. The true parameters of the Cambridge grading system, they're honestly kind of hidden in plain sight. To clear the examiner firewall, your foundational code has to rely on absolute precision. And we aren't just talking about knowing your basic identities here. The syllabus strictly dictates causal relationships and integration. So for example, if you can link the asymptotes of a reciprocal trig graph to calculus limits, you are going to achieve significantly higher marks. It's really all about connected logic, not just isolated rote memory.
If you actually want to deploy a flawless solution, you absolutely have to hit 3 specific target cognitive domains. First up, knowledge and understanding. That means defining sec, cosec, and cot without a second of hesitation. Second is application. Taking those definitions and successfully applying them to completely unfamiliar contexts or totally novel geometric scenarios. And third, analysis. This is where you evaluate the data, break down complex multi-part proofs, and strategically choose the most efficient mathematical pathway. Top-performing students, they exhibit a connected understanding that seamlessly executes across all 3 of these domains.
Moving into Section 2, Core Syntax and Architecture. It's time to look at the command matrix.
You know, this divide between passing scripts and outright syntax errors usually comes down to 2 very distinct coder profiles. Let's break them down. First, we have dev Alex. Now, Alex is brilliant at raw data inputs. He knows all his trig identities by heart, but his output? It causes massive memory leaks. Why? Because his formatting is a total disaster, and he completely skips presentation checks. He drops his notation, he forgets his degree or radian signs, and he literally loses easy marks. Then, on the flip side, we have dev Sam. Sam is methodical. She's fantastic at logical loops and structuring proofs beautifully. But she fails the syntax rules by providing generic, textbook answers that aren't actually specific to the given context of the problem. So, if you act like dev Alex, your sloppy formatting is going to crash your score. If you act like dev Sam, your generic answers will fail to link to the specific scenario. What you really need is the precision of Alex combined with the logic of Sam, but executed flawlessly.
Let's move to Section 3, debugging mistakes. We're going to open up the top examiner alerts. Think of these as our leaked patch notes to debug what's actively crashing student scores right now.
So, the data straight from the examiners clearly flags the top 3 memory leaks in student responses. Mistake number 1, missing proper format. Students are literally leaving marks on the table by forgetting to format their reciprocal functions correctly. It's painful to see. Mistake number 2, skipping presentation checks. This basically means dropping vital annotations in your graphs or failing to clearly present your mathematical steps. And mistake number 3, non-contextual generic answers.
The classic mistake is providing generic answers, not specific to the question context. Listen to me. Generic math is dead math. Every single operation, every identity you deploy must be tethered directly to the specific parameters of your prompt. If you're asked to solve for cosec squared theta, please don't just write down 1 plus cot squared theta and stop. Link it back to the specific domain given in the question. Check whether your answers actually fit within 0 to 2 pi. If dev Sam runs into a logic error mid-argument because her answer's too generic, we instantly deploy a patch. Think of the PL structure used in essay writing: point, evidence, explanation, link. In math, it's the same thing. You state your mathematical point, provide the evidence via your working out, explain the mathematical reasoning if required, and then link it directly back to the specific context of the question being asked. That, right there, is how you clear the examiner firewall.
All right, system pause. Before we push this final patch to secure maximum marks and dive into our problem-solving algorithm, you need to optimize your system feed. Subscribe to Ace the Exams right now, that's at Ace the Exams, and turn on all notifications. We drop weekly system updates to make absolutely sure your exam logic is always running at peak efficiency.
Resuming with Section 4, the problem-solving algorithm. Let's deploy the ultimate procedural framework to guarantee you capture every single available method mark.
You really have to treat every multi-part problem exactly like a script. Step 1. Deconstruct the prompt. Extract all the relevant data, constraints, and variables. Step 2. Solve systematically. Break the problem down into logical loops. Don't just jump from line 1 to line 5, okay? The examiner needs to see lines 2, 3, and 4. And step 3. Evaluate. Always check your final output for reasonableness and make sure you justify any recommendations or mathematical conclusions.
In Cambridge exams, method marks are literally your safety net. They're awarded for the process, even if your final calculation has a minor bug. To consistently capture these, you need to extract relevant data meticulously. Next, select an analytical framework. Ask yourself which trig identity actually solves this specific problem. Then execute with crystal clear notation, no skipping steps. Finally, present everything with the correct terminology. By deploying this exact framework, you shift from just blindly guessing the math to executing a foolproof high-scoring algorithm.
All right, we've reached Section 5, compiling your final code. It is time to enforce strict conventions in our interactive beta testing arena.
There are strict presentation conventions you absolutely must follow. Run a quick mental scan right now. Imagine you're running a code review, and you are handed a student's exam paper on reciprocal trig functions. Could you spot where it fails the system standards? Your headings must be proper. Your terminology has to be exact. You need to distinguish between secant and cosecant perfectly. Your formats must be mathematically appropriate to the context, and your annotations, especially on coordinate geometry graphs, they must be clear and logical. Anything less than that, it instantly triggers a syntax error from the examiner.
So, ask yourself this ultimate question. Have you evaluated alternatives, compared approaches, and justified your recommendations? Because the highest tariffs in the 9709 syllabus require higher-order assessment. Your code isn't fully compiled until you push your answer from basic descriptive math to fully evaluative logic. Did you choose the most efficient identity? Did you explicitly prove why another approach would fail in the specific quadrant? That level of depth, that is how you achieve true mastery.
Okay, let's pull everything together. Here is your final cheat sheet architecture. This is the ultimate text string designed to prevent formatting leaks and maximize your procedural method marks. Number 1, memorize the precise definitions of sec, cosec, and cot. 2, vigorously connect those concepts to unfamiliar contexts and other syllabus modules. 3, always check your format and presentation conventions. Seriously, do not be a Dev Alex. And 4, link every single step directly to the specific scenario right in front of you. Do not be a Dev Sam.
Our system is fully patched and totally ready for deployment. The bugs in your trigonometry algorithms have officially been squashed. But let me leave you with this final, provocative thought. If you treat your next exam paper just as a simple test of memory, you are going to fail the system syntax. But if you start treating it as an algorithm just waiting to be flawlessly coded, how high could your marks actually scale? Hit that subscribe button, practice those past paper questions using your brand new procedural framework, and tell us your subject and level in the comments below. We'll see you in the next Masterclass Explainer.